welcome everybody. This is the third and final industry engagement workshop for the next generation carbon capture study that AECOM have undertaken in partnership with the University of Sheffield for BEIS. So today, Stephen, if we could go to the agenda, please. Thanks. Yeah, just run through an introduction for those of you who haven't attended one of these workshops before. That'll be about 10 minutes. Then we'll talk about some of the work packages. So that's the review of the next generation technologies. We'll talk about a concept for a pilot plant. And then move on, and the bulk of the discussion today will be about the outputs of the techno-economic assessment. And I just want to say that we'll be taking questions in chat as we go today. So please feel free, we'll keep the window open as something comes up. We'll then pause at natural breaks. And obviously it's a rather long workshop, so we're going to take some breaks as we get to them. Okay, thank you. Next slide, please. So for context, the project partners are the Department for Business, Energy and Industrial Strategy, and we have some BEIS representatives today. I think Nick Bevan we've got from BEIS today to take any questions for BEIS. AECOM have done the study, and we've been partnered with the University of Sheffield, who have been very kind to organize and run these workshops for us, and also are our independent peer reviewer of the technical outputs of this study, which is the Next Generation Technologies Review. So as well as the formal project partners, there was the advisory board, and that comprises various trade body members, which we'll bring up shortly, individual technology providers who are developing and hoping to bring to market these next generation technologies, as well as the workshop participants and the wider kind of industry like yourselves. So next slide, please. All right, so here's a list of representatives on the external advisory board. And so we've got here the group that were very kind to attend the various meetings throughout the review, assessed the outputs of the study, and gave views as to the methodology of how we run the study. And yeah, I won't go through them one by one, but I just want to thank everyone for supporting this study. Yeah, thanks. And next slide, please, Stephen.
Hi, Clint. Right. Apologies, everybody. I'm now in. Do you want me to take over from here? Thanks for
that. Would be great. Sorry, we had some IT issues. Andy, please, over to you.
Yeah, for some reason why I wasn't able to dial into the Zoom, whereas everybody else clearly has. So we're up and running now. So apologies for that. Yeah. So just really the last slide of the introduction, actually, that I've now taken over. So thanks, Clint, for that. Yeah, and thanks everybody for attending on Andy Cross. That hopefully those of you who have been on previous meetings will know me as the project manager for delivering this project to BEIS. So to quickly restate the objectives and scope for the study, for those that haven't been on one of these calls before, there are three main aspects of the study alongside the stakeholder engagement, which Clint just talked you through. Firstly, we undertook a review of next generation carbon capture technologies, building on work previously undertaken for BEIS and the IEA GHG. By next generation, we are referring to technologies that aren't yet demonstrated at commercial scale, which probably means most things that aren't based on a static absorber with an amine solvent. And a review focused on technologies that may be ready for commercial deployment in the time scale of 2030 to 35, so in the next 10 years or so. The purpose of the review was to summarise as comprehensive a selection of technologies as we could, although I probably appreciate there will be some omissions, some earlier stage technologies. We looked to consider their development status and also the key opportunities and barriers to their deployment of the specific technology with their individual pros and cons. Following on from that, we undertook a more detailed review, including techno-economic assessment, of a representative selection of those technologies, identified as being most promising. and applied them to a selection of power industrial applications. The results of that are the main focus of today's call. Alongside those work streams, we developed a concept for a mobile solvent testing unit, or pre-deployment verification unit as we've called it, with the principal objective of being to indicate how early deployment of a solvent-based carbon capture plant in a particular industrial application might be de-risked through extended duration testing at a representative scale and for a representative flue gas. And really the underlying objective across all of this is to provide background and data to industrial operators, technology providers, or organisations such as yourselves that may be considering submitting funding applications for projects in the Innovation 2.0 Call 2 that was launched at the beginning of the month. John Gordon and Nick Dunn from Phase will be saying a little bit more about that later in the call. So moving on to the next slide, I think that takes us on to kind of the main body of the presentation today, or the first part of that. And I'll hand you over to David Mainio, who's going to talk you through the review of next generation technology. David, thank you very much.
Okay, thanks very much, Andy, for the introduction. So towards the beginning of the assignment, we conducted a review of next generation carbon capture technologies. This provided our team with a really good solid foundation for completing the rest of the study. Some of you may have heard us talking about this review in a previous workshop. So today's introduction to the review is going to be shorter, but even if you've heard it before, it provides a good background for when we go on to talk about the techno-economic analysis later in the afternoon. So next slide. So when you're considering carbon capture technologies, there's lots of new technology concepts out there, but it's important to remember that in certain industries, carbon capture is actually already done, or not done, but actually very easy to do. And these industries are industries where CO2 is naturally produced in a concentrated stream. So these are things like brewing and distilling, upgrading of biogas to produce biomethane, and chemical manufacturing processes that involve producing hydrogen from methane. So whilst the volumes of CO2 are limited from these sources, these are, if you like, low cost, low technical risk, easy sources of CO2. It could be very valuable when transportation and storage infrastructure is developed. They can act as a base for the market and shouldn't be forgotten about. Another part of this review was we used our experience from other innovations and other technologies to add some text on how to achieve cost reductions through innovation. So there's more detail provided in the report, but some of the key points were some innovation is achieved through incremental improvements to existing concepts. So you can have a concept and just make it slightly better through lots of incremental improvements. And this is a valuable way of producing innovation. Examples could be cost reductions in wind turbine design over the last 10 to 15 years have basically been achieved through incremental improvements of existing concepts. In addition to that, you can come up with fundamentally new concepts. And in carbon capture, at this point in time, there's a lot of different concepts being proposed. So the point that we were trying to make was there's value in supporting the development of new concepts, but there's also value in supporting the incremental improvements to existing concepts. These are both possible ways of doing innovation, but they need to be understood and treated slightly differently. Another important point when you're trying to encourage efficient innovation is the understanding of risk. If you want to innovate and do things that haven't been done before, you have to take some level of risk. Otherwise, progress will be very slow indeed. But what's important is that you understand how much risk you're taking. Because if you take too much risk, you're likely to get failed projects. And failed projects, as well as wasting time and money and resources, they slow down overall innovation in the sector. So to get this balance between too little risk and too much risk, something that's really important is understanding the risk that you're taking at any point in time. And this is done through effective due diligence, which can be done by consultants or other suitably qualified individuals. And sometimes it can sound complicated, but sometimes it can come down to really simple things like the critical importance of understanding the difference between a demonstration plant having been constructed and a demonstration plant having shown successful sustained operation for a particular technology. Next slide, please. So when we did the review, it was based on literature and speaking to various individuals with knowledge of the field of different carbon capture technologies. We looked at all the different technologies available and we split them out into 3 categories. So the first category was demonstration stage. And there's a definition of all the categories is provided in the report. But broadly speaking, the demonstration stage technologies are fairly close to being ready to roll out at large scale. So we've classed them as likely to be able to be deployable at 1,000 tons per day scale by 2030. And to get into this category, you have to have a reasonably large demonstration plant in existence that has also operated successfully for a sustained period of time. And our findings were that in this category, it was mainly amine-based solvent systems. Now, these systems have been around for some time in one form or another. But when we're thinking about innovation, we think it's important not to think that there isn't room for further development. That we would say there's lots of areas in which the amine-based systems can be further developed and are likely to develop as the technology is used more. The next category was development stage technologies. So these are a slightly earlier stage of development. They might have, or they will have a demonstration or a pilot plant, perhaps at a smaller scale, or perhaps one that has operated, but not on a consistent basis. These are more likely to be deployable at 1,000 tons per day scale by 2035. Although, as of course, when you're predicting the future, there's always uncertainty. If one of these projects were to receive sufficient funding and all of the tests were to go well, then of course, deployment could be earlier. In this category, there's a wide variety of different concepts. So we've got non-amine solvents, solid sorbents, fuel cells, membranes, oxycombustion, and alterations to processes. So there's lots of different types of process with potential advantages over the amine systems. However, these potential advantages, there's also uncertainty because of the stage of development of the technologies. And the last category was research stage technologies. These are more at the laboratory or very small pilot project stage. Some of these technologies may be new concepts, but many of them are new components. And in the case of a new component, let's say it could be an additive to a solvent or a new type of membrane. If these components slot into a larger technology platform, then it's also possible that they could be commercialized quite quickly if they can be added to an existing plant. Next slide, please. Okay, so the report also covers opportunities and barriers. So I won't go into all of the detail in this presentation, but in the report itself, we cover opportunities and barriers for carbon capture, and also opportunities and barriers specific to certain industries. So what might be an opportunity for, let's say, brewing and distilling or cement manufacture or chemical manufacture that's unique to that industry. Having an understanding of these opportunities and barriers is important because it gives you a more informed opinion of how and when this technology might develop and what can be achieved when it does. So if we think about some of the high-level opportunities, many large industrial companies that operate in large industrial processes will have decarbonisation as an important part of their corporate strategy. Carbon capture is one way of achieving this decarbonisation, and taking active steps to lower your carbon emissions can have positive impacts on the reputation of the organisation. If, and it's expected when carbon price rises, so the price of emitting CO2 to the atmosphere rises, if you've found a way to decarbonise your process, this could give you a competitive advantage. If you're taking steps to develop carbon capture projects at your sites, it's also an investment opportunity to bring money into the business, because further processing and the construction and operation of this equipment requires investment. So it's a way to attract money to the business. And lastly, on this opportunity slide, we've got ability to operate. It's possible as the years pass and restrictions on carbon dioxide emissions increase, that some industries simply will not be allowed to operate without sufficient decarbonisation measures taking place. So this may sound quite dramatic, but if we were to go back, let's say 15 years, and say that the entire coal-fired power generation industry in the UK could be shut down, that would have seemed dramatic, and it happened quite quickly, in part driven because of concerns about CO2 emissions. So this is just to say that the economic landscape can change quite quickly, so it's very important to consider decarbonisation, carbon capture as a tool for doing that. Next slide, please. So what are the barriers? What needs to change for carbon capture to be deployed more widely? A very important one is the cost of emitting CO2 to the atmosphere. These plants prevent the emission of CO2 to the atmosphere, but they cost something to run. So it needs to be economically viable. For it to be economically viable, there needs to be a sufficient price paid for emitting CO2 to the atmosphere. Second very important barrier is the availability of transport and storage infrastructure. A capture plant on its own is of little value if you don't have something to do with the CO2. So at this point in time, there's no transport and storage infrastructure in the UK. But similar to developing mechanisms for applying a cost to emitting CO2 to the atmosphere, there's lots of steps being taken to develop transport and storage infrastructure. Many people on this call will be aware of the work the UK government is doing to develop these carbon capture clusters at industrial centres, and this type of activity is likely to lead to carbon capture and storage infrastructure being more widely available. Another barrier we've got here is alternative decarbonisation options. Now this is rightfully included in a list of barriers for the development of carbon capture. But for any specific industry, this should really be seen as an opportunity. Carbon capture is one method of decarbonisation, but it's not the only method. And in some industries, you might find that other methods can be done either with lower cost or lower risk. So this could be things like fuel switching, perhaps using hydrogen or electrification, or alterations to the process, or reducing demand for certain products. So this is a potential barrier to carbon capture in some instances where other options are available, but it's also should be viewed positively, because if there's an easier way to decarbonize, then that should also be used. The last barrier I'd like to mention is technology risk. These capture technologies are often large process plants with a certain degree of complexity to them. And because it's a new technology, there's risk associated with it. Now, that's where companies like AECOM come in, our engineers work with these technologies, and we are able to understand and suggest ways of mitigating the various risks. Of course, risk cannot be removed, as with any business activity. However, the ability to understand and manage these risks is how this barrier can be addressed. Next slide, please. So, as part of this assignment we've been doing for BASE, we had 2 industry workshops. This, of course, is the 3rd industry workshop. During the industry workshops, we've had useful feedback. Some of the feedback is written at the end of the work package 2 report on the review of next generation technologies. During the workshop on the 20th of January, we requested videos from next generation capture technology suppliers, and the names are there listed on the slide. CO2 Capsule, Sea Capture, Calyx, Fuel Cell Energy, Carbon Clean and 8 Rivers. So these are just a brief introduction to these technologies, and they're still available on using the link provided. They're quite interesting videos. Of course, these are the technology suppliers' views of these technologies, which is slightly different to an independent consultant's views. But we were happy with the videos that came back, and we think if you're interested in these technologies or interested in just learning a bit more about the technologies that are out there, we would recommend watching these videos. So that brings us to the end of just a quick run through what's in the review of Next Generation Technologies report. Are there any questions at this stage?
Thanks, David. Yeah, I think Tom Jumar's put a question in the chat about why 1,000 tonnes per day as the scale, identifying that there are some industrial applications where you know, the full capturing all the emissions will be significantly less than 1,000 tonnes per day. I think the intention of that is that it's indicative of, you know, the sort of the order of magnitude of the scale of capture required for a lot of applications. Some of them are much larger than that. You know, large scale CCGT, utility scale CCGT is 6,000 tonnes per day, and appreciated, yeah, some applications are smaller, but as an indicative scale for the different applications that we've looked at in the techno-economic assessment, we've looked at different, you know, actual capture rates in terms of tonnes per day, but as an order of magnitude, it's not 1, you know, which is a pilot scale. It's not 10, which might be a demo, or 10 or 100, which is a demonstration scale. It's up to sort of full commercial scale, where we're capturing CO2 from the full flue gas flow. So hopefully that answers that question for you, Tom. I think there's another question from, is it John Williams, about the cost of decarbonisation.
Just quickly
Sorry.
say something on Tom's question.
Sorry, yeah.
So, and can I just quickly say something on the earlier question? So, from a base perspective, all the technologies we looked at, we really wanted it to be widely applicable to different sectors and applications, and so hence why we took it all the way up to 1,000 tonne a day, to make sure that it's widely applicable, and that, you know, if it can be scaled down or if it's applicable for the lower scale, that we kind of cover both bases.
Great, thanks, Nick. Yeah, so I think that there's another comment about the cost of decarbonisation and the effect on the competitiveness of UK industry. I think that's probably it's a very good point, but it's probably a question that's sort of outside the scope of this report. We're looking at development of carbon capture as one of a suite of decarbonisation options, and looking at the relative merits of different potential capture technologies. Ultimately, yes, there'll be a balance between the cost of emitting CO2 and the cost of capturing CO2, and globally, hopefully, as the market develops, that'll be reasonably consistent. But again, I think that's a wider issue.
I think probably an important point to add on that is, again, it hasn't really been part of this study, but there's been talk about cross-border carbon tariffs. So if you start to get taxes imposed on goods imported and exported to countries based on the CO2 emissions associated with those goods, which certainly has been discussed, and I can see it being brought in the future. If the UK were able to produce goods with a lower associated emissions of CO2, then that would be an advantage. Of course, it needs that scheme to exist, but it's one of these schemes that is being worked on by a number of parties.
Great, thanks. I think it's probably enough on. Thanks, David, and thanks, John, for your question. Richard Nimmons has dropped a note in about work being done by Carbon Capture Scotland, and I think that's probably relevant to where we're talking about the fact that Carbon Capture Scotland own and operate carbon capture equipment and adapting for easier integration into multiple industries. That might be quite relevant to the next section of the presentation, actually, where Clem's going to talk to us about the pre-deployment verification unit. So maybe some more to talk about on that when we get to that. And Tom Dumas followed up on his point just to say that, yes, there are some technologies that will never scale to 1,000 tons per day, but will be very applicable at lower scale. And I think I'll tell you, yeah, we've tried to kind of identify that in the technology review, and certainly when we get onto the assessment, where we've looked at the pros and cons of different technologies and the scales at which they may be deployed. So hopefully that become clear in the detail of the reports that are on the BEIS website. So if there are no more questions in the chat, I presume, Clem, I don't know, hopefully Clem said in the introduction, yeah, the intention is because of the number of people who've got on the call and the engagement, the difficulty of managing the engagement. Hopefully you could, if people can put their questions sort of in the chat as we go along, then when we get to the question sections at the end of each at the end of each part of the presentation, we'll run through them and try to elicit some discussion from there. But if there's no more specific or other questions on the technology review, then I'll hand over to Clem McKenzie, who's going to talk us through the pre-deployment verification unit concept. And I'll hand over to you, and hopefully we'll have a discussion about that once you've been through that, Clem. Thanks very much.
Thanks, Andy. Stephen, can we have the first slide, please? All right, so thank you. So the purpose of this task was to outline a reference case study for a carbon capture demonstration plant for BEIS to use really in assessment of next generation demonstrator plants that might be coming forward seeking BEIS funding in the future. So how much might these projects cost? How long would it take to implement them? What kind of outputs could they produce? And to answer these questions, our task was to develop a concept for such a facility. The objectives of this case study were, first of all, identify the scale at which to target the demonstrator unit. From that, estimate its cost and programs, how long it would take to build, how long a test would run for, as well as the outputs that you could get from the selected case study. So these decisions involved a bit of iteration with the advisory board, with BEIS themselves, with our other external stakeholders to select a configuration that really provided an optimization between value for money, rigorous study outputs that are applicable to, say, a targeted full-scale unit on that site, and what might be a representative or an outline of what might be a credible project in its own right. And just want to highlight the fact that there was a bit of iteration, you know, so the cost and schedule obviously increase the larger you build a plant, but the outputs, once you start to approach the full-scale unit, will you're getting quite similar data, so it was finding an optimum in the selected configuration. And so that led us to the kind of outputs that we would like to see from such a unit. So the target was selected to be processing a variety of real flue gases in situ for an extended run, so on the order of about a year, around about 8,000 to 10,000 hours perhaps running cycle. And that this unit would be flexible to be modified to meet site-specific requirements. So, for example, if there is no steam on the site, you could adapt the unit to take a package steam boiler, for example. And if there's changes with the flue gas concentration, you could modify the key equipment to accept the different concentration of CO2 for a specific site. But ultimately, you're starting from the same rig that has the same test data, it has the same ability to test realistic reclaiming strategies. So you go in with the plan of, we'll be running we'll be running the reclaimer continuously, we'll just be doing it in batches or something like that. And as well, the flexibility to drop in and test alternative solvent formulations. So this would be wrapped up in what we're referred to as a pre-deployment de-risking or pre-deployment verification package, rather than, strictly speaking, kind of a pilot plant. And the idea is that you, as an operator, get a unit before you invest in the full-scale plant. You have this thing, much like, say, in the desalination industry, you get a pilot that would run for a year before you build the full-scale desalination plant. A similar sort of thing here. Okay, so the next slide, please, Stephen. What is the value of this unit? And really the key risks that are targeted, we've broke them down in, you can get the full table in the report, and this is just a summary here. So kind of separating them into critical risks, which would be ones that don't just stop at the site boundary, they may affect multiple plants. They may even go as far as affecting kind of public money in if multiple projects end up carrying these risks and the risks are borne out and they have to shut down multiple projects potentially, then you may end up with a shortfall in the amount of CO2 that's shipped through a cluster. And at least the way the business models are set up at the moment, then government carries some of the risk in the CO2 shipping capacity. So the way you get around this and where the value comes in is both to individual sites from not going out of business and wider is to identify before you invest in the full-scale unit whether the assumptions you have about the full-scale unit regarding the pre-treatment, regarding the energy performance, regarding the formation of the waste are correct, or if you need to make some modifications, and you make these modifications before you commit to investing in the unit. You get an idea of the project OPEX that you might expect in the full-scale unit. And that's useful both for both for individual sites and then also to government to have this data available, because it really needs to be, in a lot of cases, site-specific and over a long period of time. Then we have the medium risks. So these are the things that don't in themselves necessarily cause an immediate showstopper problem, but things like exceeding environmental permit conditions. If the say the post-treatment of the flue gas doesn't pick up some contaminants, and you pick up during the course of a de-risking study that you're producing something that you need to treat. So things like that. And then also there are potentially some marginal benefits to in the course of running the de-risking campaign. And this would be things like identifying where you've maybe overspecified some equipment or packing, and some things are running a bit more reliably than you expected. So you can feed that back into the design, as well as if you find that the waste you're producing is perhaps non-hazardous and your conservative assumptions going into the design were perhaps not necessary, as well as, and this is the final thing I'd like to say on this slide, the marginal benefit of testing advanced operating strategies, advanced process control strategies, testing things off design and seeing really how you can go from we've gone from a threshold of talking about 90% for a lot of cases. Now we're starting to talk about, as an industry, about 95%. But as we get left with the last few percent as the threshold capture rate, the off-design performance really becomes more important. So these are transient things, startups, shutdowns, and so on. So being able to test these things on a simulation of the full-scale plant will come in quite useful to sites themselves. And next slide, please. So here's the block flow diagram. It is for the concept that we've developed for this work package. It is here as an example. I'm not expecting you to be able to make out the text. You can find it in the full report if you are interested. The main thing to highlight here, and what is perhaps less expected, is the splitting of the absorber column into 3 smaller columns side by side. And so the flue gas goes up through one column and into the bottom of the next column and into the third column. So it's split in series rather than in parallel. And the idea for that is that you have the absorption all done within the first 2 columns, and then you have a third column for doing washing and post-treatment. And this way, if you are trying to deploy on a site where you need to respect the current site's visual impact, this is a way of minimizing the visual impact. So this concept also carries on through, on the right-hand side, all the way to a liquid CO2 product that you, over the period of time, you test and you verify that it does meet whichever spec you're trying to target. And fundamentally, you could target a sales grade CO2 with this package. So you've got deoxygenation and dehydration to produce sales grade CO2. So that's about it on the block flow diagram. Next slide, please. Right, so the outputs of this work package. The 3 things: the scale, the cost, and how long it would take. The scale we chose was around 5 to 9 tons per day. The reason for that was to do with the minimum diameter of the stripper column that we see as the kind of the minimum threshold of giving representative packing performance. And it depends on the flue gas composition. So this unit would expect to do about 5 tons per day on, say, natural gas, say CCGT type flue gas, up to 9 tons a day when the flue gas is more concentrated, and that's the range. But the key parameter being set is a 0.4 meter diameter stripper column in this unit, which is containerized, much like the image you have here is of a pilot plant in the US at NCCC. And although you can see the column there is quite tall, so if you imagine that split into 3 in series, but in the right-hand image, fundamentally most of the unit lives within a shipping container. And that's the point behind keeping this unit quite small, that you can have it modularized, turn up to site, and you just need to assemble it and connect the interfaces. So the cost has been calculated, scaled from previous project data, plus or minus minus 50 plus 100% class 5 cost estimate, has been estimated around about £4 million. And that is for, say, one version of it, so either targeting a CCGT flue gas or an energy from waste flue gas. And that's normalized to £20-21, so not taking into account any of the recent changes to commodities and markets. So for the program, we estimated for this package a feed and kind of engineering studies of about 4 months, followed by about 12 months of engineering and the construction and the fabrication and shipping, and then about 1 month on site to commission the unit. So that is followed by a 12-month testing, de-risking campaign. And so altogether, just over 2 years from deciding that you want to do this to the point where you have the data that available for you to use. All right. Thanks. I think that takes us to the next slide. The next step. So given that this, the design of this unit is complete, and its purpose was to inform what might a typical project look like, some potential further steps are, finding willing host sites, people that are interested in having such a unit would be a next step to developing this further, notwithstanding the fact that that would be outside of the study, which, as I said, is now complete. Then, getting into establishing funding for FEED and for the next phase. So any future BASE competitions. Then getting on with the design and specifically making any modifications for the site's requirements, and then determine contracting strategies, because obviously there's a lot of moving parts to working out a pilot plant that then that does a 12-month testing campaign and working out what to do with it afterwards. So I think that is it for this slide. Stephen, can we have the next slide, I think, which should take us through to discussion. I think, Andy, would you like to take through some questions?
Thanks, Clint. Yep. Hopefully everybody can hear me now, by the way, after the feedback, after my
that's much better.
Far into the introduction. Yeah, I've switched my headset, so hopefully that's okay now. Yeah, so we've had a few comments in the chat. There's a sort of an ongoing discussion about sort of business models and monitoring and measurement of CO2 emissions. So I think I'm gonna leave that to sort of play out in the chat, because it's not directly related to what you've just been talking about, Clint, but there's a couple of questions that are. So David Cowdery has asked, what is the percentage target for successful capture of CO2 for the assessment of a new plant or technology that will be approved? And I think you talked about capture rates and sort of ambitions for capture rate for amine plants earlier on, but I think the specific or particular point in that is whether there's a sort of a minimum or target for capture. I think for this plant, as you said, it's an amine plant on amine solvent plant on either industrial or CCGT type or gas turbine type flue gas. So 95 and upwards are what we kind of are starting to expect from the capture plants. Other technologies in other applications are potentially very different depending on the limitations of the technology and of the host plant in being able to provide a thermal or electrical power to to drive the capture plant. Do you have anything else? Any other comments on that, Clem? Anything else to say?
Oh, that's fine.
To that? Yep. And David's also asked about an acceptable limit for down days for the CCUS plant for regular inspection. I think that's kind of wrapped into the availability and overall kind of annual capture rates part of the the objectives or the benefits of the pre-deployment verification unit is that it allows those sorts of issues to be tested and demonstrated at a pilot scale for the specific solvent or the specific technology and the specific flue gas. So where we come into reclamation strategies for the solvent or impact of flue gases and contaminated solvents on material selection or what have you. That's sort of part of the objectives associated with that. I think it's fair to say, Clem, would you?
Yeah, I think the main thing, especially if we're talking about the context of the pre-deployment verification unit, you would choose and do a reliability, availability, maintainability study through the design to match whatever the host site runs. So if the site is, say, an energy from waste plant and it runs 8,000 hours a year, you make sure that you have a capture plant that can also run 8,000 hours a year. There's not much point having the capture plant be more available than the host facility, but there is obviously a problem if you can't get test data and the host site is running, but you need to take the pilot offline to clean the exchangers.
Okay, thanks, Clint. There's another question from, excuse me a moment, Kazim Adadokan. What are the technological considerations that have been developed regarding new plant and existing plant in the CCUS model? So I'm interpreting that, and please let me know if I'm wrong, is a question around application of carbon capture to new build plants as opposed or compared to application of carbon capture to as a retrofit to an existing plant, be that power, energy from waste, or an industrial plant. In the benchmarking, sorry, in the techno-economic assessment work that we've undertaken, the scenarios have assumed for different applications, whether it's a new build or a retrofit plant, but there are specific issues obviously around retrofit, principally about, again, interfaces with the existing plant, flue gas ducting connections, and particularly steam offtake, where heat for the process has been taken from the host plant. For this unit that we're talking about here, I think it's fair to say the assumption is that it's retrofit, and there will be, while it's trying to be as modular as possible and as and broadly mobile, so to be deployed at different plants, that site specific interface work to provide the electrical and heat thermal energy for the process is a critical part of the deployment to a specific site. And I think there are cases where potentially the work required to be able to retrofit something potentially becomes almost prohibitive in terms of the amount of work that they would need to be done on the host plant to be able to integrate it, and that those are the sort of site specific issues that are kind of the next stage in the development of a concept like this, where we've tried to look at in this study we've looked at the generic concept, but there'll be site specific applications of that. Sorry, I'm trying to talk and read the questions at the same time. There's a question from, not sure if that's Chris or Chris Roberts, apologies. Are there benchmarks or targets for energy consumption per ton of CO2 captured and sequestered or utilized? We haven't identified in this study particular benchmarks or targets for that. That's one of the key metrics that we've used to look at the technologies, but that's probably something we can come on to in more detail when we get to the full techno-economic assessment. Work, and I think
I've got one from Baljeet Singh. So how many cycles of adsorption and desorption using aqueous amine solvent? So the absorption with amines, it's not there's no simple answer to that. The question is about the contaminants that make their way into the solvent and how you reclaim it. And you may have more or less kind of for the pilot unit concept, we assumed that you would be reclaiming continuously and constantly taking out the contaminants and repairing the solvent. So it's not really a cyclical process like solid sorbents, excuse me.
Great. Okay, thanks, Clint. Tom Dumar has asked a question about whether exceeding environmental permit conditions is not a critical risk.
Yeah, I'll take this one as well, Andy. So yes, certainly it's a challenge for an individual site, but the critical risks that just want to highlight that there's a difference between an individual site exceeding its environmental permit conditions and potentially having issues with operability, and multiple sites going out of business, and the impact on the taxpayer. So that the critical risks are things that don't just stop at one site. The medium risks are the ones that stop at one site. So that's the difference between them.
Great, thanks, Clem. There's also a bit of discussion on the chat on regarding digital twin and predicting amine degradation reliably, which I think John Gibbons has responded to on the chat. But John, I don't know if you want to say a bit about that while or on that point?
Yeah, I mean, just very quickly, certainly from the research projects that I'm involved in, you don't see much reliability in predicting or in matching degradation behavior between different applications. Even when you're trying to make them similar, there's a lot of things going into degradation. And when you're looking at particularly dirty flue gases, things in them, a lot of the time you don't even know what's there, and you won't know what's there over a period of a year as things change. So it will be very difficult to get reliable results. Boundary Dam, for example, at coal plant, was getting very different solvent management costs than they predicted, and I think so was Petronova before it closed. So we're just not there yet. Yeah. I see Eric's point about a solvent can often stay in operation without too much intervention for 6 months. That's true. Boundary Dam had a honeymoon period of, I think, about 6 months before it all started to go pear-shaped. Certainly one of the tests I've seen using MEA at RWE's plant at Niederhausen, they ran MEA with very little degradation for 6 months, and then it went exponential. The degradation went exponential, and it was very, very hard to stop it. So I think the idea with solvents, as far as I can see, is the best thing is not to let them get to a very degraded state, to keep them clean, if you possibly can. So reclaim frequently, really. But we'll see. We'll see what happens when people manage to do it successfully.
Yeah, that's what this concept is intended to address, isn't it? Yeah. There's also a comment about the cleanup of flue gas from something, for example, coal-fired generation, and again, yes, that's a significant issue. The condition of the flue gas that goes into the actual absorption stage. Certainly, again, in the techno-economic assessments that we'll come on to shortly, the flue gas cleanup or pre-capture polishing has been considered specific to the applications we've looked at, but it's very much part of the issues associated with different plants and application to different industries and applications. And I think I'm just going to take one more question now on this chat, because I think it would be good to then take a break and move on to kind of the main body of today's presentation, which is the techno-economic assessment. But Richard Heath's asked the question about moving forwards with the development of systems cater for a plant that might be high CO2 emitters when running, but are not working on a 24/7 basis, e.g. 8 to 12 hours a day, 5 days a week. Flexibility of CCS plants a key issue at the moment. AECOM and the University of Sheffield are involved in a project with BASE and SSE to look at flexibility of kind of utility scale CCS plants for a dispatch where a CCGT is running in dispatchable mode. There's also many.
Yeah, I'm just putting a link for that in the chat, Andy.
Great, thank you. Okay, thanks. Yeah, flexibility is obviously also relevant to a number of other industries, and the key issue there is in terms of the the thermal cycle and reclamation, or regeneration of the solvent. Yes, it is an issue. Most of the work that's been done to date assumes baseload operation. That's not how a lot of carbon capture plants are going to operate, and that flexibility and means for doing that either by solvent storage, where you just have a reservoir of lean or rich solvent to be able to accommodate the startup and shutdown, or preheating or heat storage of some description, or alternatively, what one of the potential solutions or contributory solutions is smarter heat integration, which I think also plays to one of the questions that's been asked there. And are all part of kind of the optimization and the development, incremental development that David talked about earlier, that's inevitably going to come once the first projects are up and running, and you can actually see how they operate. So unless there's anything that anyway in the chat that I've missed that we really want to cover now, I'd suggest that we'll take a quick sort of 5 or 10 minute break at this point. So thanks very much for your discussion and engagement on that. And I think it looks like we're going to have a lively afternoon going through, some of these very significant issues associated with the deployment of carbon capture across the various industries. But we'll perhaps take a break now and restart maybe around 2:10 because we've got a lot of content to get through in the second part. So we'll probably best to have a short break now. Given the Okay, welcome back, everybody. I was just waiting for the clock to tick over to 10 past. So hopefully we've got everybody back with us. So the next section of the workshop will be a presentation by David on the techno-economic assessment work that was undertaken as part of the next generation carbon capture study. David's going to sort of go through the methodology and approach that we took to the benchmarking and assessment of the next generation technologies, and sort of summarize the results that hopefully everybody's had a chance to look at within the reports that have been published on the BEIS website. But this hopefully will give you some sort of background and context to that. And then the remaining part of the afternoon will be comments, discussion around those, and any questions that you may have about the approach that we've taken, or the results and the relative comparison between the technologies. So I'll hand over to David then. I think, as you may have noticed from the timings on the start of on the agenda, that the anticipation is we may finish a little before 4 o'clock, but we have that time available if the discussion runs on and we need that to get through everybody's questions. So thanks very much, and I'll hand over to David for the next part. Cheers. Thanks, David.
Okay, thanks very much. So the techno-economic assessment was quite a large part of the assignment. It's also quite an interesting part. During this assessment, we started to look at costs, but also drilled down into some more detail about the opportunities and challenges for applying specific technologies to different industries. Next slide, please. So this is the type of study that the scope could have grown in all sorts of different directions. And this slide is basically to remind people that what we did was a study on carbon capture. The study didn't look at transportation, storage, or utilization, which are important for the development of carbon capture, but they've been covered by other studies. It wasn't the focus of this study. Also, we didn't look at other ways of decarbonizing industrial processes, so things like fuel switching, efficiency measures, demand reduction, or process developments. Again, these are important and should be considered in conjunction with carbon capture or as alternatives in some cases, but they were not the purpose of this study. So the approach we took was to investigate quite a high number of scenarios. We've looked at quite a few different technologies and applied them to different industries. So this approach has an advantage in that it allows comparisons to be made across industries and between different technologies. So it's good in that respect. Where the limitation occurs is that because we've looked at a lot of scenarios, and of course time and budget are always limited, there's a limitation as to how much detail we've gone into with each scenario. So they're quite a high level of project definition on each one. These aren't full feasibility studies or full engineering designs or anything like that. Another important limitation to note at this point is that these are all emerging technologies. And for emerging technologies, there will always be limitations in data availability. Sometimes it might be legitimate reasons of commercial confidentiality, with providers not wanting to share everything in a report that's going to be published publicly. But quite often it might be because the data simply does not exist at this point in time. An example of that could be, what is the long-term maintenance cost of a component that has never operated for a long time? So this limitation in data availability has to be considered in relation to the results achieved. Next slide, please. So this graph is included in the report, and it is of gas prices. So it's really there as an example of volatility in the energy market. Equally, we could have shown a graph of electricity prices or oil prices or coal or any energy commodity. It's basically meant to say that energy markets are volatile. And carbon capture is a technology that's related to energy. The main operating cost tends to be energy input to capture the CO2. So we've conducted our study, and in our study, we've made certain assumptions about the cost of energy, and we've detailed what they are and where they've come from in our methodology report. But of course, if the cost of energy changes, the outputs to the study will change, and that's important to remember. Just before we move on from this slide, the slide is saying that the cost of energy is difficult to predict, but important for the viability and the cost of carbon capture. Another price that's also very important is the CO2 emission price, and it is arguably even more difficult to predict. So when you're considering the viability of carbon capture and the timeline and speed and scale for deployment, it's really a combination of the CO2 price and the energy price. Both of these are important factors. Next slide, please. Okay, so what did the study do? If you've looked at the reports, you'll see there's different scenarios. So we've got benchmark scenarios and scenarios looking at next generation technologies. For each one, we've done, they have the similar structure. So there's a description of the technology. You'll see basic process diagrams. There's also text provided on things like what flue gas pre-treatment is required before the core capture technology. What are the energy requirements? What's the development status of the technology? And various other bits of useful information. Then we've calculated the levelized cost of capturing CO2. That's a cost in pounds per ton of CO2. So to do that, what we've done is we've calculated capital costs. So that's a capital cost that includes everything from the host plant to the transportation network for the CO2. So the capture equipment, CO2 conditioning equipment, and the flue gas cleaning equipment, it's all included. We've then calculated operational costs, so fixed and variable operational costs in line with the inputs used in the methodology. These are then put into a fairly basic financial model, which has been generated specifically for this project, one for each scenario, using Microsoft Excel. The last thing to say about levelized cost of capture is it relates just to the cost of capturing the CO2. There is no cost in the levelized cost of capture for residual CO2 emissions to the atmosphere. So let's say if a capture technology captures 95% of the CO2, which is common for most of the scenarios studied, there might be a cost associated with emitting that last 5% of CO2 to the atmosphere, and that's not included in the levelized cost of capture. The next thing we've calculated is the impact on product cost. So this is, if you take the cost of the product without carbon capture, or the market price today, basically, and then you add the cost of capturing the CO2, and you also add a cost of residual emissions to the atmosphere, and then you get a new product cost. Now, we've added a cost of residual CO2 emissions to the atmosphere, but that's not the price companies pay today. This is a CO2 price that came from BEIS, and it's intended to represent what the CO2 price might be in a net zero business environment. We've given commentary on opportunities and challenges for each scenario. Now, this is often spread throughout the write-up, so there'll be ones about energy use in the energy use section, or flue gas treatment challenges in that section of the write-up. And finally, comments on uncertainty. This is just a high-level look at where the modelling uncertainties lie for each technology. It's designed to help readers think about where the risk might be for the different technologies and the different scenarios. The next slide, please. So when we're thinking about the performance of next generation capture technologies, we wanted to compare them with something. So for that, we developed benchmark scenarios. We selected 3 industries, so gas power, generation, energy from waste, and cement. These industries were selected because, one, they're quite likely candidates for carbon capture in the future. And 2, we thought the challenges of applying carbon capture to these industries are representative of the challenges faced by a broader range of industries. So these are things like different challenges associated with getting the required amount of steam, or challenges associated with cleaning complex flue gases that have a variety of contaminants in them. For the benchmark capture technology, we've selected amine solvents. So just going through this diagram very quickly, in an amine solvent system, the flue gas will come in from the host facility. It'll be cooled down before passing into an absorber column. In the absorber column, the flue gas passes upwards, and a solvent, amine solvent, is flowing down the column. When these 2 fluids come into contact, carbon dioxide is dissolved in the amine solvent. The flue gas coming out of the top of the absorber column has most of the carbon dioxide removed. At the bottom of the column comes out solvent, which has CO2 dissolved in it. That's the rich solvent as labelled on the diagram. This solvent is then heated in a stripper or a regenerator column, and the CO2 is liberated. It can then be conditioned and compressed and sent for transport and storage. This then creates a stream of lean solvent, which goes back to the absorber column. And this is the basic process in an amine capture plant. Next slide, please. So here are our levelized cost of capture results for the benchmarks. Now, there's quite a bit of information in here, but just a few comments that I think are worth making. If you look at the dark green stripe at the bottom of the 3 bars, this is the capital cost. And you can see it's lowest on the gas, followed by cement, then energy from waste. So it's the same capture technology in each case. These differences in capital cost are largely driven by economies of scale, with the gas power plant being the largest application, followed by cement, followed by energy from waste. Another important difference which creates this difference in results between the 3 industries can be found in the lime green stripe in each of the bars, and this is the steam supply cost. Now, steam supply cost in the gas power plant is considered to be the lowest. This is because the gas power plant we've studied is a new build plant. So it's relatively easy to get the required amount of steam. If you know what amount of steam is needed, then you can design your turbine and your steam system to supply the required amount of steam. The energy from waste in the cement scenarios are retrofit projects. And depending on the conditions at your site, it might be much more challenging to get the required amount of steam, let's say, at an energy from waste plant. An energy from waste plant, of course, has a Rankine cycle, it has a steam system, but it was most likely not designed to have this volume of steam extracted from it. So you'll need to modify it, and the modifications could be quite expensive. So we have assumed a higher thermal energy cost, and that's led to this difference in results. And of course, cement plants generally don't have a steam system, so would require a different source of low carbon heat to power the carbon capture plant. And that is the higher cost assumed there. Now, what is the cost of supplying this thermal energy, the energy from waste or cement plants? Well, that will actually be very site specific. So it really depends on your particular plant. If you were to develop a carbon capture plant in one of these industries, one of the first questions you'll be asking is, where are we going to get the required energy from? What will be the cost of heat and how much is available? How are we actually going to get it? A couple of other points to make on this slide just before we move on. We've talked before about the volatility in the energy markets and how this will impact the results. The gas power generation is the lowest cost of capture of these three benchmarks. But of course, if gas price changes, let's say it increases, as has happened quite markedly over the course of us doing this study, then the cost of running, operating and capturing the plant at the gas power plant it would increase. And finally, before we move on, the gas benchmark assumes constant baseload operation. And for many gas power plants, that will not be the case. They'll run in peaking operation, only providing power at times of high demand. So if the gas power plant was to run in peaking mode, the carbon capture asset would be utilized less, and we would expect the cost of capture to rise. So that's an introduction to the benchmark results. We'll now go on to talk about some of the next generation technologies.
Going to dip in there actually, David, yeah, because we've had a few comments and questions come up in the chat related to the methodology, so it's probably best to sort of cover those off as we go before we get into the main one. So I think there's a dialogue going on around the availability of information from existing CCS projects and what from that is available in the public domain and what isn't. I think the approach we've taken to maintenance costs, which is the original question, is spelled out in the methodology report that's been published, and I think John Gordon has sent put the link to that report in the chat. But broadly, we've taken a fairly high-level view of maintenance costs, typical for sort of costing a process plant as a percentage of the capital cost of the plant, as an annual cost, and that's outlined. Most of the kind of maintenance items are relatively kind of standard, process plant equipment. So that's been adopted as, and a lot of this has been done, maybe not as accurate as it might be, but as David said in the introduction, it's been a fairly high level assessment of a large number of scenarios. But the important thing is we've made sure that they're all compared on a consistent basis, with specifics for the different technologies addressed where relevant. Mark Summerfield asked about whether we're looking at.
It's very, very hard to get published data on costs for comparable flue gas capture applications. I mean, there's everything I could find in the BAT review that I put a link for in the chat, but it's tricky.
Yes, absolutely. Yeah,
there's some quite big numbers out there as well when things go wrong.
Well, yeah, and yeah, much of what we've done here assumes that the plants work and operate kind of as intended and as you would hope for a process plant of this complexity. Sorry, so Mark Summerfield's asked about whether we're assuming it retrofit or new build, and David, I think you've covered that since Mark posted that. So the benchmark is, sorry, the gas is assumed to be new build. The energy from waste and the cement is retrofit, really because of the UK market and the most likely sort of host sites for carbon capture for the different applications. Baljit Singh has asked about solvent regeneration using solar concentrated devices. I think that and we've tried to provide configurations that we think are kind of typical and representative of what's likely to be deployed in the UK market. So, you know, that there may in a project specific instance be the potential for that, but we you know, it perhaps not as generic as it might be. I think.
Yeah, I think that's an example of there's lots of different ways you could supply low carbon heat, and if you're developing one of these, that's an important point to consider, but it hasn't been the focus of our study. It could really easily turn into a whole study on sources of low carbon heat. We've tried to pick a reasonable number for the purposes of a cost number for heat, for the purposes of comparing the carbon capture technologies.
Thanks, and that's particularly relevant for the cement benchmark, where there isn't a huge amount of residual heat to drive the capture process. Brian Sweeney's asked a couple of detailed questions on the LCOC calculation on the basis of the methodology. Hopefully that's answered in the chat and in the methodology report that's on the BEIS website. The LCOC is the divisor is the total CO2 captured, albeit discounted over the lifetime, which is the standard BEIS methodology that's been adopted in comparable studies. So that's the reason we've adopted that. And sorry, just scrolling through some of the later excuse me, the later comments added. Sorry, Tom Jumar, the capex for the EFW appears higher than for gas. Is that due to the mods to the steam cycle and flue gas cleaning? Can you comment on the capex for the capture unit between gas and EFW in view of the difference in mole % CO2 in the flue gases? I think you did discuss the relative difference in capex for the different plants. David, have you got any more to add on that?
Yes, basically, I think that the prime driver is economies of scale. I think the gas power plant is 6,500 tonnes per day of CO2 capture, and being the largest of the three, and the energy from waste is coming in at around about 1,000 tonnes per day CO2 capture.
Great. Okay, thanks, David. Pierre's asked about estimates of error bars and sort of uncertainty within these figures. That sort of a detailed kind of sensitivity analysis was beyond the scope of what we were able to do in the study. The cost estimates have been based on sort of the bottom end of a class 4, top end of a class 5. So that's the sort of the capex range that of sensitivity we're talking about, and you know, the sensitivity and the accuracy of the other estimates that hopefully is covered in the detailed methodology report that you'll find. Michael Whitehouse has asked, does the cost of steam take into account loss of generation for CCGT? Essentially, yes. The steam supply cost is essentially the opportunity cost of the lost generation revenue, both for gas and energy from waste. Energy from waste is proportionately higher because you're just, you know, the jet power is generated purely by the steam cycle. So you every ton of steam you take out of that reduces commensurately the generation. Question from Ignacio Rabsian about these being FO, first of a kind or nth of a kind costs. I think we're at, David, I'm going to have to check with you on that, actually. I know we talked about this, and I can't remember where we ended up in terms of how we've assessed the capex and where we think that is in terms of.
Yeah, I would say it's probably better to consider them as nth of a kind, but we did actually purposefully steer away from that terminology in the report, because you immediately run up against this issue of, well, is it the anticipated first of a kind cost, or is it the actual borne out in practice first of a kind cost? And these can be quite different. So these costs, I would say it's better to consider them as probably an nth of a kind, as in if it's built and it is built as anticipated and it works as anticipated.
Great. Okay, thanks, David. And I just, before we move on, comment on Kazim Adadokan, you've sort of highlighted that it seems like a reasonable methodology, but there are specific issues around for individual industry participants on plant operability. I think, yeah, we would highlight, and I think David sort of said in part of his introduction, that we tried to adopt a reasonably robust, consistent methodology across all the plants, albeit with limited data and performance data for developing technologies that haven't been demonstrated at the scales we're talking about. So yeah, that these are so those limitations kind of stand in the figures we've put together, but we would anticipate that any site-specific project or any specific project would need to consider the specifics of the application and the technology and the host facility to to develop a business model for a specific plant. So with that, I think if you're happy to move on, David, thanks very much for your comments and questions, everybody. Hopefully we're clarified the methodology. We can go on to show how that's been applied to the next generation scenarios. Thanks.
Okay. So the first technology we'll look at, this is quite an interesting one. It comes from a company called CO2 Capsule. I'll probably just start by running through this process diagram. It looks complicated, but it's actually not all that complicated. Flue gas comes in from the host facility, it's cooled down, it's then compressed. So it goes up to the compressor, and the next two boxes along are heat exchange steps. So they're just cooling the flue gas down, and it then goes into an absorber column. So this absorber stripper combination is very much like the amine plant we looked at before, except the difference being it's a different solvent. So it uses hot potassium carbonate, and it's under pressure. When the flue gas with the CO2 removed comes out of the absorber column, it then goes through a heat exchange step, and before being emitted to the atmosphere, it runs through a gas expander. Now this allows recovery of some of the energy used to compress the gas, and that can be used to drive the compressor, to contribute to the energy use of the compressor. So what are the advantages of doing it, of taking this approach? Well, one interesting advantage is that it only requires the energy input is in the form of electricity and not steam. It does require some steam, but that's generated inside the process. So if you're at an industrial site where it's difficult or expensive to get a sufficient supply of steam for other technologies, then this plant can be operated on electricity instead. Another advantage of this is the different solvent. It's hot potassium carbonate, which is a non-proprietary solvent, so it can be bought from a number of different sources, and it's less toxic and less harmful than some of the amine solvent blends. What are the limitations? So one limitation is there has been limited testing of the complete system as operating as a whole. But what I should say is that this really applies to all of the next generation technologies. They're all at some stage of having done some testing, but there's limitations in that testing. And also we are aware of CO2 Capsule are taking steps to develop testing units which can be deployed at specific sites or on a not full scale, but a slightly smaller or intermediate scale. And this is exactly what they should be doing. This is taking the testing forward to the next step. Another potential limitation in the technology is compressor availability at very large sizes. But that being said, there are some big compressors and expanders available on the market. And of course, if a larger size is required, multiple units could be used. In terms of applications, our study has it applied to the gas power generation and energy from waste sectors. So there's two scenarios using this technology. However, equally, it could have been applied to the cement sector. It's just we were limited in the number of scenarios to include in the study. In fact, it might have worked quite well in the cement sector because in that sector, there's not a ready supply of steam. And also, our gas power generation scenario uses a combined cycle power plant. So that's a gas turbine with a steam cycle using the hot exhaust, recovering more energy from the hot exhaust of the gas turbine. This particular capture technology could be applied to an open cycle gas turbine. And then more energy would be recovered from the heat of the exhaust by the CO2 capsule equipment. So this scenario is described in the report section, but it hasn't been included as a separate scenario in our study. If we move on to the next technology, next slide. So the next one I'm going to talk about is the use of a non-amine solvent. The one included in our study is by a company called Capture. So a non-amine solvent, it uses a process equipment setup that's very similar to the amine solvent system. So the concept's the same in that you bring the flue gas in, you cool it down, you then have an absorber column where the solvent is contacted with the flue gas, and then a desorber column. And in many ways, it's a similar concept. And that's an advantage because it's not a whole different process that's being invented. Another advantage, or the main advantages of this system, is that the solvent claims to have improved properties over the available amine solvents. So these improved properties allow reduced energy use, reduced hazards associated with solvent toxicity and the toxicity of breakdown, solvent degradation products, and also resilience to degradation. So if this different solvent chemistry has these advantages, then that's a valuable innovation. What are the limitations of this technology? Well, there's been limited testing of the solvent in different applications. We know that Capture has done extensive testing. They've worked with Drax and done other testing as well in their solvent. But there are limitations in that testing as to the application in different industries. But again, as we said before, this applies to all of the next generation technologies to some extent. And like CO2 Capsule, we understand that they're taking steps to work on further testing, which is exactly what should be done for the development of the technology. Now, the reality is with testing, even if the initial testing looks good and very positive, you cannot predict with certainty the outcome of further testing until that testing has been done. So let's just say for a minute, now we have no reason to suspect that this will be the case, but let's just say for a minute, some of the tests don't perform as well as expected. If that was the case, the concept is still valid. So the idea that something other than an amine could be used as a solvent is still a valid concept. Capture may well be able to tweak their solvent or find an additive to improve the performance, or someone else might find one. But fundamentally, the idea of finding a different chemical that has better properties in certain applications or in many applications is a valid area for technical innovation. Next slide, please. Okay, so this next concept, something to say straight away is that it's not strictly a capture technology. It's a process alteration that makes capture easier. And it's, in this study, applied to the cement industry. So I'll try to explain it. This might be a lot easier to understand if you've got some knowledge of the cement industry, but I'll try to explain how it works. If you go to the top of the diagram, you see limestone coming in. That's the basic feedstock for cement. It's milled and it's dried, and then it moves down to a preheater. Once it's been preheated, it then continues down the line. In a normal cement process, it would go into a bit of equipment called a pre-calciner. And in this equipment, further heating would occur and CO2 would start to be released in a chemical reaction. So the limestone is basically calcium carbonate. When CO2 is released, it produces calcium oxide. And that's one of the core components of clinker, which is then used to make cement. So what the LILAC process does is, instead of having a traditional pre-calciner where hot combustion gases are directly mixed with the powdered limestone, it separates these two components by putting the powdered calcium carbonate, powdered limestone, inside a tube and applying heat to the outside of the tube. And what this does is it means when the CO2 comes out of during the chemical reaction, it can be collected in a relatively pure form rather than being mixed with combustion gases. And this becomes much easier to capture. So what are the advantages of this? Well, one advantage is that much of the energy used to run the LILAC reactor would have been used anyway to run the pre-calciner. So the net energy use is actually low in comparison to other means of capturing CO2. A similar advantage would be that if it were a new build plant, or you were anyway needing to replace your pre-calciner, you're saving money by buying this and not having to buy a traditional pre-calciner. So the cost of the traditional pre-calciner could be subtracted from the cost of this technology. Now, what we should say is in our study, we've assumed a retrofit project on a cement plant. So that's not what's been assumed in this study, and it's not what's been assumed for any of the scenarios. But particularly with the LILAC process from Calix, that's a potential advantage which could make the results better if it was a new build or pre-calciner was needed in anyway. So low capital cost and low energy use are very interesting advantages. What are the limitations of this technology? So it needs to perform well as a pre-calciner. Some testing has already been conducted. There's a LILAC 1 demonstration plant, but there are limitations in that testing, similar to the other next generation technologies. There are plans for a LILAC 2 project, and if this project goes well, many of the limitations will have been overcome. We'll have more information about the performance of the unit as a pre-calciner and certain other important aspects of how the unit works. A second limitation that's important to note is that it only captures process CO2 emissions. So emissions from the combustion of the fuels aren't captured because they are on the outside of the tube and they go up the stack like the emissions would have in the cement plant previously. So these emissions can either be released to the atmosphere with an overall reduction of around about 60% because the process emissions are captured, or a second carbon capture technology could be added, something like a solvent-based system. Next slide, please. So here we have the overall levelized cost of capture comparison results for the study. Now, there's a lot of information on this chart, so I'm going to break down talking about it over the next few slides. At this point, just to introduce you to it, you can see the benchmark for the gas is the very leftmost bar. If you move along 3 bars, you get the benchmark from the energy from waste. Then you see the different energy from waste scenarios that we studied. And then you get the benchmark for the cement and the different scenarios. So if we go on to the next slide. In the report, there's important footnotes underneath the chart. And today I'm just going to talk about a few of them. The levelized cost of capture is just relating to capture. So there's no CO2 transport and storage cost, and there's no cost for residual emissions, as we've mentioned before. The capture level varies between the scenarios. So I would say most of them capture 95% of the CO2, but not all of them. And it's listed in the report which ones don't, and that's for various different reasons. Some of the technologies don't just capture carbon. So we talked about the lilac technology being a pre-calciner, and that's important to note. It isn't just a capture technology. So in some ways, comparing it directly to other capture technologies has its limitations, because it also, its performance as a pre-calciner is also important. Fuel cells also come into this category because they are doing something different as well. They're generating electricity from gas. And last important footnote before we go on is that the levelized cost of capture is only one aspect of technology performance. So the LCOC results don't take any consideration of things like environmental performance, and they're limited in the way they consider things like to what extent a particular technology has been demonstrated. Next slide. Okay, we'll now talk through a few of the results. The two that are highlighted with red circles or red ovals around them are advanced amine systems. And you can see they're compared to they sit immediately to the right of the relative benchmarks for gas and energy from waste, and they're better. So in some ways, it's an important result. It's perhaps not that surprising. What we're basically saying here is that if you take amine systems, there are still improvements that can be made to them. So these could be improvements in things like solvent chemistry, additives, different blends. They could be improvements in the process, such as energy recovery or different improved ways of measuring and managing the solvent health. Or there could be improvements in things like construction. Another point to note on the advanced amine systems is that these are often supplied by large multinational companies. So this can be an advantage when it comes to things like financing the project, because it can help if the technology comes from a company with a large balance sheet, and then they're at least able, in theory, to take an appropriate share of the risk. We haven't done an advanced amine system for the cement industry, but that's not to say that it couldn't be applied in the cement industry. It is just due to the limitations in the number of scenarios that we could study. Next slide, please. Okay, so the two bars now that are circled are the hot potassium carbonate. So this is the technology we talked about a few minutes ago. And this is quite an interesting result. If you look at the gas, hot potassium carbonate gas scenario, it's performing in a very similar way to the benchmark, and even on this result, maybe slightly worse. Whereas if you look at the energy from waste one, it's a real improvement. It's a significant drop relative in levelized cost of capture relative to the benchmark. So what's driving this? Well, to some extent, it's the concentration of CO2 in the flue gas, with it being more concentrated in the energy from waste example than in the gas, and that suits this technology. But also, it relates to the cost of energy. So the cost of thermal energy in the energy from waste scenarios is assumed to be higher than in the gas scenarios. But this technology doesn't use thermal energy. It uses electrical energy. So it doesn't have that disadvantage. And that just shows that this technology has potential advantages when low-cost thermal energy is not available. A couple of last things to say before we move on, talking about this result. Again, it could have been applied to the cement industry and might have worked quite well because the cost of thermal energy, assumed cost of thermal energy is high there. And finally, yes, as we mentioned before, the result in the gas power generation industry was when it was applied to a combined cycle gas turbine. If it was an open cycle gas turbine, then the results may well have been, or would have been different and could well have been better. Next slide, please. Okay, so these two results that are circled now are for energy from waste, and they're solid sorbents and membranes. And if you look at them, if you cast your eyes along to the benchmark, they aren't particularly impressive results. They're roughly the same or maybe a little bit worse. But the point I'd like to make here is that how well something like a sorbent or a membrane system performs is very dependent on how well the actual sorbent or the selected membrane performs. So what's the cost and what's the performance of these core components of the system? And if improvements are made, and we know, for example, in solid sorbents, there's lots of research work going on. People are looking at things like metal organic frameworks, which could offer improved properties. If new sorbents or membranes can be developed, then these concepts could be much more competitive. I should also say that in terms of other carbon capture applications, so upgrading of biogas to produce biomethane, people do commercially use sorbents and membranes. So that's a slightly different process, because instead of separating the CO2 from flue gas, it's being separated from biogas, which contains a high proportion of methane. So it's a different separation process, but it's to say that they are valid concepts and they can have opportunities to develop them further in different applications. Next slide, please. Okay, so the two that are circled now are molten carbonate fuel cells. And these results have come out very well in this analysis. A couple of points to note here. As we mentioned before, these aren't purely capture technologies. They take natural gas and they generate electricity. And as part of that process, the way that the fuel cells can be set up, they can capture CO2. But these levelized cost of capture results, because of the way the analysis is done, they are impacted by the economics of gas-fired power generation in a way that the other technologies aren't, because they're not generating power from natural gas. So it's just something to be aware of, that if the economics of gas-fired power generation change, let's say there's less of a difference in price between gas and electricity, then the economics of using a fuel cell to capture CO2 would also change. And of course, like the other technologies, testing is limited in representative applications. Fuel cells require a relatively pure, well-cleaned flue gas to go into them. Our study assumes quite extensive equipment before the fuel cell to do that cleaning process. But until you've actually built one of these and operated it in the long term, there's uncertainty as to exactly how much equipment you need to achieve this long-term steady state operation. That's the end of the levelized cost of capture results. So other results that we produced in the study were related to the impact on product costs. So if you look at the vertical axis, this chart relates to the cement industry, and it's the price of clinker. Now, just for anyone that's not familiar with this, when you're making cement, most of the cement is made from a substance called clinker, and that's the energy intensive component of the cement. Clinker is then mixed with various additives to produce different grades of cement. But our study considers the product to be clinker because that's the energy intensive component. If you look at the bar on the left, this is the unabated example. So if you don't have a carbon capture plant, the green stripe at the bottom of the bar is the product market price. So that's the current product market price. At this point in time, the cement industry doesn't pay for emission of CO2 to the atmosphere. They're awarded credits, free credits under the emissions trading scheme. So that's the current market price, the green stripe, and it's the same across all the scenarios. The large pink stripe that sits on top of it is the cost of emitting all of the CO2 associated with producing the clinker to the atmosphere. Now, of course, the size of this pink stripe depends on the carbon price. And the carbon prices we've used, they come from BASE, but they aren't the current emissions trading prices. They are a price that's really meant to represent what it might look like in a net zero business environment. So if we then move to the left, the next bar is the benchmark. So at the bottom, you've got the product market price, and then you've got this yellow stripe. And the yellow stripe is the cost of capturing the CO2. The pink stripe that sits on top of that, that's the cost of the residual emissions. Now our benchmark captured 95% of the CO2. So despite having a high CO2 price, the cost of residual emissions is relatively low. The pink stripe is quite thin. If you then move on to the lilac technology, which is the one we talked about earlier, you've got the same base cost of product. You've got a dramatically lower capture cost. And as we said before, that could be even less if it's a new build plant or a new pre-calciner is required anyway. But then you've got a high cost of residual emissions of CO2 because the capture level is lower. It's about 60% in that scenario. So that brings the impact on product cost above the benchmark. So this helps us start to think in some interesting ways about these results. Let's say everything's the same, but the price of CO2 is less. For ease of mathematics, let's say half. If the price of CO2 halves, the pink stripe on top of the benchmark will halve, which won't bring down the product cost very much. Whereas if the pink stripe on top of the lilac example halves, it brings it down, and it brings it down to well below the benchmark. Another option with the lilac plant is to build this additional carbon capture technology. So most likely, if carbon dioxide emission prices were as assumed in this chart, you probably would build the additional carbon capture technology. So the capture level in that scenario would be higher, and then the impact on product cost would be lower. So that's something that could either be done initially when the project was built, or perhaps as time progressed, if and when carbon emission prices rise. So we thought that was quite an interesting result from this chart. Of course, the fuel cell has done very well again, but again, it needs to take into account the economics of gas-fired power generation, and that's isn't part of the other results in the same way. Next slide, please. Okay, so we've done the study, we've got the results, we've looked at the results, and the question comes up of what should we do now, or what should be done now? Some of the actions are continued government action on related issues. So by related issues, I mean things like permitting, transport and CO2 transport and storage, and the development of business models so that these projects become economically viable. So that's things like applying carbon price and figuring out how it actually works in reality, and how industry still remains competitive, and how the technologies are supported. A lot of work has gone on in these areas, and it is continuing to go on in these areas, but there is further requirements in many of them. We need to not forget about these established carbon capture applications. So things like capturing CO2 from brewing and distilling, or biogas upgrading. I think there's a real place for these in the future once the transportation and storage infrastructure has been developed. And even before then, if we're able to supply the domestic CO2 market, so that's things like CO2 is used in the food and drinks industry, from a wider variety of sources, that could be valuable in relation to diversifying our supply of CO2 and making the market more secure. The next point is component testing, which Clem talked about earlier today. This topic just kept on coming up again and again, and it's the importance of representative testing of components. So not just testing a solvent or a membrane or a sorbent, but actually making the test as representative as possible, so that you know how that component would work in the same situation as the commercial plant. And doing this testing and understanding how these components work and how they degrade and how they can be maintained is an important area that will help us innovate and progress these technologies. The next step, if you like, is mid-scale demonstration facilities. So the component testing gives you really valuable information, but there's limitations on what it tells you. Mid-scale demonstration facilities, so let's say 100 tons per day. This tells you things like how construction costs might look for a larger plant, long-term availability figures, and reliability. All of these are really important, but there's limitations in what you can learn from either engineering studies on paper or component testing. And that's where these mid-scale demonstration facilities are really useful. Next slide, please. So just some final closing thoughts. Our team has spent 10 months on this study, and it's been a really interesting process, but what are some of our thoughts at the end of that? Well, firstly, the role of carbon capture. We think carbon capture has a really important role to play in industrial decarbonisation, particularly in industry sectors where limited other options are available. In my mind, it's not really a question of, is this required? There are still legitimate questions about when will this happen and what scale is it, but it really seems like such an important tool that at some point we would fully expect this will happen and it will scale up. Opportunities and barriers. So there's lots of opportunities that come out of this. There's developing new technologies, exporting new technologies, the ability to decarbonize difficult to decarbonize industries and make low carbon products. So it could be low carbon products for the UK or low carbon products for export. But of course there's barriers, and the barriers aren't just technical. They're economic, social and political as well. What we would encourage is if there's individuals on this call who are responsible for either developing policy or making investment decisions about how and when to invest in carbon capture, you should understand the opportunities and barriers available, understand the opportunities and barriers that exist, but also keep aware of how they're developing, because it is a moving picture and there's work going on all the time to reduce these barriers and encourage the deployment of this type of technology. So people who are operating in this industry really need to keep up to date with these barriers and how they're changing, what other technology developments and what other things are going to feed into this. The price of emitting CO2 to the atmosphere is clearly important. So the viability and the timeline and the scale of carbon capture deployment will undoubtedly be influenced by the cost of emitting CO2 to the atmosphere. It's currently zero in many industries, and it's difficult to predict when and how this will change. But we would say, you know, global warming is not an issue that's going to suddenly disappear, and reducing CO2 emissions is central to tackling the issue. So it would seem very likely that carbon prices will be applied and will increase for industries. So it's really a matter of when and how this happens. And the last point I was going to make on this slide was the risk of inaction. So the point here is not the point that's often made on, you know, the risk of catastrophic climate change and how it's urgent that we take actions to decarbonize. Of course, that's a valid point, but it's not actually the point I was wanting to make here. I was wanting just for a minute to forget about climate change and forget about the morality or ethics of releasing CO2 to the atmosphere and just purely think about economics. Now, investing in carbon capture, there are risks associated with it. There's a whole variety of different risks associated with it. However, at this point in time, if you really think about it, there's also risk associated with not doing it. Because let's imagine, as we expect will be the case, the price of emitting CO2 to the atmosphere rises, and your business hasn't done anything in relation to investing in carbon capture. Now, that might not be building a full plant, but let's say finding out which sites it works best on in your portfolio of assets, or doing some feasibility studies, doing component testing, developing relationships with capture technology suppliers, or perhaps outlining plans or attempting to, or building a demonstration plant, or developing a larger plant. If you've made some of these steps, that will put you in advantage over companies that have taken no action. So the closing point here really is, if you want to take the least risk option, it could well no longer be considered doing nothing. If no action is taken and you aren't in some way making progress in using this as a tool for potential tool for decarbonizing your industry, then that in itself is a risk. And that is the end of the presentation. So if we can go to questions.
Yeah, thanks, David. Thanks very much for that. A lot of content you've got through there, and there's been quite a lot of chat going on in the background alongside that. So I think we'll now kind of launch into what we're considering kind of the main kind of questions and discussion part of the afternoon. Because there's, I think, anticipating quite a lot of questions coming up through the chat. We've asked John Gibbons if you can sort of chair and marshal the discussions while I kind of moderate and pick out the questions from the chat. And if the ACON team, David, Stephen and Clem, you could kind of stick your heads above the parapet and be ready to sort of pitch in and answer some of the panel discussion alongside Nick and the BASE team and John as well. That'd be much appreciated. So thanks very much. So the first thing I was going to touch on, so we've got potentially up to 45 minutes if we want it. So hopefully we'll be able to go into some of the questions in a reasonable amount of detail. There was quite a lot of discussion going on LILAC and the carbon emissions, or the CO2 emissions from the heat source as opposed to the process. Obviously the LILAC process is designed to capture the process emissions, and Brian Sweeney pointed out that LILAC 2, the intention is that it is to consider sort of a fuel agnostic, or look at operating the LILAC reactor as a fuel agnostic system. So looking at various potential low carbon heat sources. Yeah, we're aware of that. Very good point. And that also speaks to your point, David, on the potential cost of the residual CO2 emissions if they're not captured. So that you noted the potential that to retrofit carbon capture to the CO2 emissions from heat generation as the price becomes prohibitively high. Similarly, that might prompt a switch to a low carbon heat source, be that hydrogen or biomass or electrical heat from a low carbon grid. So I think there's been some other chat in there, but I think that covers most of what was talked about on Lilac. I don't know, Brian, if you have anything more you want to say on that, or clarifications or discussion of the approach you're taking with Lilac 2.
Just a tiny moment, if I may. First of all, thank you very much for your careful study and all of that description of it today, which is very, very interesting and very valuable. But secondly, on Lilac, we have already quite a lot of experience of electrical heating of the calciner. We've had a plant with electrical heating running for a couple of years now.
At what scale, Brian?
It's a small scale plant, but it's demonstrating the feasibility, if you like. It's about 20 centimeters diameter and 25 meters high, something like that. We have design ready to build for hydrogen heated or electrically heated. So that's all, if you like, ready to go. Working with other fuels is very much part of the thinking on Lilac 2, which is an upscale and looking at basically using the same fuel as the cement plant uses, whatever its mixture of coal and RDF and other things may be. In the fullness of time, we'll get to increasing the RDF percentage of that, but that's again part of the Lilac 2 project longer term.
And Brian, have you looked at capturing, if you're using a fossil fuel, well, or any fuel to fire, I suppose, have you looked at capturing the CO2 from the heating?
Oh, absolutely. That's what Lilac 2 will do. Yes, exactly that.
And how do you propose to do that? How are you looking at doing that?
That's an extremely good question, and there's a great deal of discussion going on at the moment. The base one is to use lime, so to have a limestone lime circulation, but also looking at collaborating with some of the other capture technologies where there is a significant saving from 35 or 40%, or going down to 35 or 40% of the capture requirement, simply because it's just the heating CO2. So at the moment, that all bets are open and being discussed.
Okay, thanks.
Great, thanks, Brian. Thanks, John. There was one other question that came up. Theo Chronopoulos asked a question on the solid sorbent. Actually, sorry, before I come on to that, I was just going to clarify that in the Lilac scenario that we looked at, the heat generation was by essentially the same fuel mix as we assumed for the benchmark, which I think was a combination of biomass and coal, which was sort of through discussion with the Mineral Products Association considered to be kind of representative of what the UK industry typically does at the moment, but wouldn't be the the fuel as we go through into a low carbon future. But that's what the CO2 emissions and the associated with heat generation are based on in the scenario that's in the study. So just to clarify that.
In addition to that is, of course, that the RDF has some bio components, but that's fine print, as it were.
Yes, and that's something again we haven't considered in the study, because it's it's a whole different world of thing. The relative the difference between biogenic and fossil carbon, and the capture of that, essentially, if we're talking carbon credits in in a low carbon future, then it's anticipated there won't be a distinction. If you're capturing biogenic carbon, then that's even better. Okay, sorry, I was then going to move on to the question raised by Theo Chronopoulos about the solid sorbent case and what we've assumed in terms of which solid sorbent is it. So I think it's fair to say it's not intended to specifically represent a proprietary technology. We've developed a sort of a model for a generic solid sorbent technology, which is based on representative sorbent performance for the flue gas for an energy from waste plant. It is assuming a rotating bed for capture and desorption of the CO2. So the and the capex and opex and performance of that plant has been based on kind of a comms assessment based on kind of literature review of a number of different sort of sorbent technologies that are in development. David or Stephen, do you have anything else to add on that, or does that sort of essentially sum up what we've done?
Yeah, so it's a more generic case than some of the more specific technology applications, and there's obviously a range of different sorbents, and some of them are more appropriate for different flue gases. And in this instance, we've just used a more generic case.
And again, I think it's a key area of kind of development in terms of the, as David described, the sort of component testing that different sorbents designed for different flue gases, different CO2 concentrations, and particularly if we're talking about energy from waste or biomass or other industrial applications with different levels of contaminants and sometimes kind of very variable and unknown contaminants in them. That's an area where sorbents, I think the main area of development for sorbents as we go forward into the next, developing the next generation technologies.
And other things, Andy. A while ago, Eric Silver asked about sources of information, and
I was going to come on to that one next, so thank you.
Yeah, is there a difference between the open campaign? Well, he says there's a difference between open campaign data and vendor claims, and have you got consistent data? And I guess you try to get use public domain data where feasible, but I don't think it was always feasible, was it?
We haven't used any proprietary data. We've deliberately not entered into NDAs with any of the technology providers. So everything that we presented has been based on public domain data or publishable data. For many of the cases, that has been based on information provided to us by the technology providers. So their performance predictions and capex and opex figures, particularly capex figures for a plant of the scale we've talked about, which as David highlighted is sort of in most cases beyond what's actually been demonstrated physically in pilot plants and demonstration plants. But yeah, a large part of what we've done is review of that. The large part of the work that's gone into the study is review of that data, making sure it's presented on a consistent basis between the different scenarios, and making sure that we're kind of validating and critically assessing the performance claims and making sure that that they do seem reasonable and they are consistent with public open campaign data that we've seen and our understanding of the differences between the technologies.
I guess just to add, obviously with this type of study, with any study in emerging technologies, the availability of data is going to be a challenge. Another way we have tried to add value is in the report, there's sections on modeling assumptions. So if there's areas of data that we're maybe less confident with, we've given that data a lower quality rating, just to highlight to the reader that there's definitely uncertainty in that area. Or if it's data that we are more confident about, then it'll have either a medium or a high quality rating.
So, I mean, I guess you explained it, but it maybe is worth talking about again. On the amine solvents, the improved or advanced, which you called it amine solvent, isn't a specific solvent.
That's right. It's an averaging out of the different developers.
Yeah.
And yeah, and I probably would say that, yeah, that's an indication of where the industry anticipates it getting to in 10 years or so. So yeah, those amine compositions don't exist at the moment, but that's kind of where the industry is hoping to get to. Well, yeah, not that they've told anybody yet.
Who knows?
Yeah.
So that one is it isn't really a supplier. It's only some of the other technologies.
One of the key issues there is in the cost of reclamation and the stability of the solvents, and it's a large part of that the development work is going into that rather than necessarily into the actual thermal performance of it, kind of as you touched on earlier on.
And some of the other technologies, I guess, were referenced in Bayes KKDs, weren't they?
Yes.
So there will be other information there. So I think that's it's fairly well referenced in terms of where you can get the information. But yes, nothing's entirely consistent because we don't have plants to look at. We don't have the experience. We're still predicting.
Yes, which is part of what made the project very exciting. Yeah.
and I guess that brings us back to one of our main recommendations of the next steps, which is component testing. Which, if it's done, it brings the next improves the quality of the data available in the future.
Yes. I've got a question for Nick. Actually, you put it in, Nick. What's IFP?
Yeah, it's the Industry of the Future program, where
so again, sorry?
It's the Industry of the Future program,
right.
where we are doing blank sheet studies. So if it's fuel switching, CCUS, energy efficiency, resource changes, it's looking at the full gambit of different low TRLs, rather than being pigeonholed into silos. And so Atkins are doing that on behalf of Bayes.
So will they be taking results from this project? Is that the?
I hope they are. No, yeah, no, they will be.
Okay, interesting. We've got a question. I don't know whether anybody's here on food grade CO2 in small amounts. Any comment on that? Otherwise, I guess I do a quick answer.
I guess I can start, John, and then you can pick up anything on this. So in each of our benchmark and next gen simulations, the flow sheet did include post-treatment of the CO2. There's challenges at the moment with, especially with waste-derived CO2, ever marketing that, just regulatory challenges marketing that as food grade. But I'd just like to stress that a lot of the food grade CO2 that you do see, that does come from post-combustion capture today. And likely, if you're buying tomatoes, they've probably been grown in a greenhouse that is CO2 enriched.
Certainly in the summer, yeah. That's right. People sometimes use the gas heating in the winter. In the summer, they're definitely using it. And it will, certainly if you're buying Dutch tomatoes, then some of them will come from CO2 generated energy from waste plants. Pentair Union, who provided the Tata Chemicals plant that's gone online recently, have got a reference list of some tens of plants of the order of 100 tons a day, just in terms of the scale. Okay, David Cowdery, you've got a hand up.
Yeah, first of all, great presentations from everybody, really, really good and really interesting. Looking at the testing that you've done about the different sorbents, their effectiveness at CO2 capture for different processes. And I'm doing future predictions here. So in the future, do you foresee that Bayes will introduce regulation recommending obviously the better sorbents which are available for different processes, to maximize CO2 capture rather than leaving it to the market to decide?
So I think putting the business models to one side, which is
Nick, Nick, excuse me, you're a little bit quiet. Is there any way you could be louder? I don't know if you can turn your mic
yeah,
up.
unfortunately, my headset's broken.
Okay, no, that's a lot better actually. Thanks, thank you.
So if you put the kind of business models to one side, which are basically helping industry to make investments and get on with doing CCUS or fuel switching or other things, so then you can begin the process of learning. Eventually, there will be some form of market-orientated approach, be it a carbon price or a border adjustment, where industry will again make decisions around what's the best capture rate, efficiency for the different processes, and the market will, assuming there is some kind of international consensus around the price of carbon. So that, I guess that's the way the British systems have always worked, where we intervene, we step back, and then let the market get on with what it's meant to be doing, so long as it has the right price signal, the right value signals going into the market.
I think I would say though, with a lot of these things at the moment, if you don't see long-term test results on your own flue gas for sorbents or solvents, then you may get surprises when it's tested. It's the whole business about
and we have to be fair, the Americans and others have thrown the kitchen sink at solvents, solid sorbents, membranes, that and so there has been a lot of effort doing it, and we're starting to see that kind of the shortlisting of technologies that have survived that process, and we'll continue to see it. But one thing is that we're doing with the 4 CCS clusters, that we get on with deploying the equipment and then allow these iterative or disruptive technologies to slowly filter through.
Yeah, but I mean, just as I say, just to comment that, going back to what you use, the PDVU concept was there for a reason. Somebody had their hand up, but maybe it went down again. Kazim, I didn't catch your name. Is it still there? Yes.
Kazim.
Want to ask you a question?
Yeah. I just want to. Anyway, great presentation. It's pretty lot of insight into it. Just a follow-up to the question you just responded to. I was just looking at the scenario where you have an open gas and a closed combined cycle, and the rate of return on both, you have an average beta under the combined cycle. And if we look at the solvent issues that have come up, whichever solvent that is being used by various industry could be some sort of returns as benefits to whichever type of technology that was used. Could that suffice in some cases? I'm just thinking with respect to that.
I'm sorry, I didn't follow the question. You're talking about solid adsorbents with gas?
Yeah, I mean, if you use different solvents, they come with different results.
Yes.
And the cost implications also vary.
I mean, all I can say is I'm not really aware of any proposals to use solid sorbents, particularly with gas turbine flue gases, because of the low CO2 concentrations that have actually got far enough to give you an idea of the cost. I don't know whether anybody else is.
We did have conversations with a few sorbent suppliers, and one of them did in fact tell us that they weren't even targeting gas-fired generation capture. They were aiming at higher concentrations from different applications.
Yes.
And that's what they were choosing to focus on, at least for now.
Yeah, that seems to be the impression. There are very large volumes of flue gas and low CO2 concentrations. Alistair, stirring it up as usual, asking about direct air capture. do you think direct air capture can ever be cheaper than point source capture? So indirect capture by the air for certain applications, is that one of the things you're thinking about? Alistair?
Sorry, John, was that question directed at Alistair? Yeah.
Alistair Rennie, yeah. He put a comment in the chat about direct air capture. Is he there? Is Alistair still on? Are you there, Alistair?
He's still in the chat, but muted.
Can we unmute him? Is he unmuted? Right. I can't see him. Okay. Well,
And I think, yeah, but from our point of view, I'd suggest that that's sort of a wider question than the scope of this study. So yeah, I think that again, as David's mentioned, there's the whole economic case for carbon capture generally, and the relative merits of point source capture and direct air capture or other greenhouse gas removal technologies to deal with the residual emissions, because even in the best case we talked about here, we've got 95% capture now. Some, as we said, some of that may be biogenic CO2, so that helps. But
I'll say on that though, that if you did have to go for direct air capture, you pretty soon crank up the capture rate a bit.
Yes,
I mean,
well, that's what we're hoping, isn't it?
I mean, certainly everybody looking at it, I think the question is, is it actually getting up to the level of the CO2 that was coming in with the air, or is it just a small amount off that? If you're playing for direct air capture, you can push things quite far.
The only thing I was going to raise, John, there were a couple of questions and a bit of discussion in the chat about fuel cells, and I think we've got Hussein on the call from FCE. So
yeah,
I think
it's about capture levels for fuel cells.
Yeah. So I think in our study we've assumed that 95% of the CO2 from the flue gas is captured in the fuel cell, along with the CO2 generated from the power generation from the methane. So that's one of the reasons that the levelized cost of capture is as it is for the fuel cell cases, because actually we're capturing a lot more CO2 than in the comparable cases.
So I suppose the question for saying is that all of the carbon dioxide from the fuel for the fuel cell? Can you come on, Hussein, and tell us? If you're talking, Hussein, you're muted.
Yeah.
Very good.
As most of you may be aware, that the fuel, the motive force for carbon capture while we're producing power is actually the fuel we put in, right? And that causes the ionic movement and concentration of the CO2. We, in general, when we say 90% carbon capture from flue gas, we completely capture our own fuel, the natural gas captured CO2 from. So in essence, when we say 90% carbon capture from flue gas, we're doing actually close to 93–94%, because we are capturing our own carbon to generate that. There was a question about the plot plan, how size it is. Of course, fuel cells are notoriously, the fuel cell power plants, notoriously, they're not as energy dense as like gas turbines, and they take some some area to basically lay down the fuel cells. For the carbon capture, we actually have developed a concept that we go vertically. It's to imagine like beehives, where we can put the fuel cells in where the bees nest. And
the hexagonal layout.
You're right. And for example, in our calculations and design work that we've done for Exxon, extensively, for capturing carbon from a 700 megawatt gas turbine combined cycle, I would say, system or plant, 700 megawatt worth of flue gas, we have been shrink down our fuel cell plot area to about 200 feet by 200 feet, just going vertical. And some of this data may be published various places. We certainly do have patents related to configuration of the fuel cells in that beehive configuration I just mentioned. Any other questions? I'll be more than happy to answer.
Were there any other questions, Andy? Particularly, I think that was the main one, wasn't it?
Those are the main ones for fuel cell. Yeah.
I think there was one related to other, demonstrations. One thing I got to mention: the core technology, the molten carbonate fuel cell, has been commercialized for 20 years, and we're using the same molten carbonate fuel cell with no alteration in our carbon capture work. So the technology, the core technology, is actually been in operation in various power plants. We have like 50 plants all over the world. So what we are doing basically right now at the pilot scale demonstrations and a couple of locations planned. One is in Canada by a bunch of oil companies involved, Shell, for example, and Chevron, and a few others in an oil sand, where they burn a lot of fuel to actually make steam for upgrading the oil sands. They generate a lot of carbon dioxide. They had interest to show that our molten carbonate is beneficial doing there. So we have a pilot plant, about 1 megawatt fuel cell plant there. Right now we're working on the design demonstration in a year and a half. And then of course with ExxonMobil, we are planning to do a demonstration in Rotterdam, one of the refineries, to do carbon capture there. So
will that be on natural gas or on refinery gas?
We will be running the refinery gas, but it would be cleaned up because refinery.
Okay. That's very good.
Thanks very much, Hussein. Yeah, I think we've probably got time for one or two more questions, haven't we, before we then need to
Nick's got his hand up.
Yeah,
I think we'll next Mark after that.
Just a quick question. So the 1 megawatt unit, will that be your lead unit you're doing CO2 capture on, or have you been doing CO2 capture on flue gases in your lab for a longer duration?
Yeah, we have part of our work, initial work. We actually took our molten carbonate. We went to the Department of Energy in the United States and asked them for funding for demonstration. And we have done years of actually testing for that, mostly focused on carbon capture from coal plant. That's what the U.S. Department of Energy, the initial interest was focused on. Now with the joint development agreement that we have with ExxonMobil, we're actually doing extensive laboratory testing, in our location. So yes, we do. And of course, there's a project we do have with the University of Sheffield in England. We already have shipped our fuel cell there. We are working with them, supporting them to build the facility needed to run the fuel cell.
Okay, Mark.
Yeah, but thank you. It's really just picking up on a comment I put in the chat in relation to next steps. Obviously within the study, and I think completely fairly, that there's various read across between your benchmarks that you suggest are also valuable for other industries or make sense in other industries. So the direct ones being energy from waste to biomass. Really a question for Vase are they going to try and sense check these results at all with the biomass industry to make sure that those energy from waste results do map across? And in conjunction with that, when looking at energy from waste, there's also the additional question of further innovation and how CCS technologies might fit on advanced conversion technologies, and whether the results for energy from waste will also map across onto advanced conversion technologies as well, which is a whole other innovation piece as well. So, you know,
are you saying do another study? Or
it's not necessarily saying do another study. I think absolutely correctly within this study, it was correct to make those assumptions, but I think there could be some sense checking done with the industries involved, just to see if they do map across accurately, and that they make sense. I don't know if it really requires another study, but that would be another next step and another piece to think about.
Yeah, Mark, I guess what we wanted to do with this study was to basically be a shop window for industry to think about different technologies that they might be not aware of, but when they're looking at potentially a second or third site, for them to consider them. But it's been deliberately designed that when the Co2 was launched in back end of May this year, that individual industrial sites can apply for funding, and John will just talk about this in a second, to get funding for them to look at some of the work AECOM's done and see if it applies to what they're looking at doing, and as well as broadening out to some of the other technologies, you know, other kind of industrial sites, be they energy from waste or biomass or cement, that they can look at, you know, using this preliminary information. So Nick, it's a fill your boots almost.
Fair enough.
Nick, on the sort of cross-checking though, do you think we'll ever know what sort of I don't know if you call them strike prices, but you know what I mean, the business model awards are to the phase 2 projects that go ahead?
I'm not sure. As you might have guessed, you know, just the learning we had from offshore wind and some of the earlier CFDs, the kind of bilaterally agreed ones, you know, will be what they are.
But they were announced, weren't they?
They were announced. So I'm not sure exactly, but eventually we will get to some form of auction system.
Yeah. My understanding on the business models is that they will be announced, even the bilaterally negotiated ones, and we'd certainly expect them to be.
Okay, well, so you better be on your toes, AECOM. They're going to see how correct you were.
Can we give just a few minutes for John Gordon just to let people know about a quarter, and they might have a few questions on that.
Yeah, I was just going to say I think perhaps we've move on to John's discussion on the sales pitch for the Co2 now, and make sure that you're able to do that. So yeah, thanks very much, John, for marshalling all of those questions, and lots to go at, lots of issues, and BEIS are offering money to people to help resolve some of those issues. So John Gordon, have you got a slide you want to share?
Yeah, sure. Can you hear me okay there, Andy?
Yeah, yep, loud and clear, thank you. Yep.
Fantastic, right, no problem. Yeah, let me just find out how to share, because I'm on the I don't think I can share on this. No, I can. It is. In BEIS, we normally use Teams. So let me just get the point up there. Brilliant. Can you see that all right?
Yep.
Yep. Fantastic. Right, okay. So first of all, I'd just like to say thank you to AECOM, to you, Andy, Stephen, Clint, and David, everyone else that's worked on this. It's been a huge undertaking over the past 10 months, as David mentioned, back in August when we started this, and also to John Gibbons as well at UK CCS RC, and then also the technology developers that have been involved in the study, and also the workshop participants and the industry advisory board as well. And we're hoping that this study can start a conversation about some of the challenges that we have within capture technology and developing that and to be deployed in the clusters, and also non-clustered dispersed sites. So I'll talk a bit about CCS Innovation 2 at Co2 that we've got on at the moment. Nick, have you given an introduction yet at all?
Just quickly, so for those who don't know me, Nick Bevan, I've been working with BEIS for the past 10 years, funding CCS innovation and trying to help the policy teams, you know, get these CCS projects off the ground and the right kind of business models in place to allow the UK to really go after CCS and industrial decarb projects.
Is it my audio that's went, or is it Nick's?
You're back now, John. Yeah, I think that was your
Okay.
cue. Step back in.
Yeah, sorry. I'm actually having an IT nightmare today. The Virgin Media van turned up about an hour ago, and they yanked all the cables out of the box. I'm using my phone to broadcast just now, so if there's any issues, bear with me on that. So brilliant. I'll move on. So just to give some policy context about CCS, obviously BEIS and UK government has been involved for the past decade on it. We had the situation in 2015 where the decision was taken not to go forward with it, but the most recent announcement really looks to the 10-point plan for a green industrial revolution back in November 2020, launched with the Prime Minister, and also coincided with the COP conference last year as well. But looking at CCUS within BEIS, within government, there was a lot of discussion on the chat about business models and regulation, and we've got the £1 billion allocated to the CCS Infrastructure Fund and SIF. We've got the Track 1 cluster announcement that was made last year with HyNet and the East Coast cluster selected and the Scottish cluster in reserve. And then we've also got Track 2 being developed at the moment. And the business models, I've posted some links in the chat earlier on, and you can find out more information about that. So that's the side of BEIS that's working on that. Looking at infrastructure and how we develop CCS regulation, and then all the environmental aspects of it, working with DEFRA, the Environment Agency, SEPA, and then also the devolved administrations in Edinburgh, Stirling, Cardiff as well. So we're quite involved with that, but where Nick and I are working in, we are funded allocated to technology so we can decarbonise by 2050, and again that feeds into the 10-point plan that we've got as well. And by taking these actions within CCS, hopefully we get to the 5th carbon budget. We see CCUS as playing a huge role in that, meeting the standards there between 28 to 36, and then also the 6th carbon budget after that for 2033 to 37. So the Track 1 cluster should be coming online by 2030, and then Track 2 2035. So you can maybe see where that changes into it. And with the CCS Innovation 2 programme, we're looking to really get the technology developed so we can deploy it at the cluster sites in time for 2030 and 2035. So there's some chat direct air capture. So the net zero different technologies and developing. There's 10 key themes that we've got there. And just to give an example, some of the funding that we've got available over the programme, it's from 2021 to 2025. We'll get advanced nuclear, looking at, as you've probably seen in the news, about modular reactors. We've got the biomass feedstock innovation programme, which focuses on bioenergy. We've got advanced CCUS, which we've got accelerating carbon capture storage technologies, Act 3, which is a international collaboration that we work with different partner nations in developing that. So that was announced in the beginning of April, and we've also got the £20 million CCS innovation programme, and then on to within Nick and I's team, more in industrial decarbonisation, looking at the hierarchy of it. We've got efficiency, and then we've also got decarbonisation and replacement rebate has now been removed, and that was done in April, so we're now looking to develop replacement technology for that as well, and the Industrial Energy Efficiency Accelerator 2. And then there's just some other programmes that we've got. We've got some programmes in built environment heat pumps, we've got offshore wind, we've got the £70 million direct air capture competition, and greenhouse gas removal, we've got hydrogen supply, energy storage, and energy entrepreneurs fund. And you can find out more information about that on the NZIP information page on gov.uk. So on to CCS within BEIS. This is the kind of profile that we've charted out for the development of the technology specific to CCUS. So CCS Innovation 2, we're really looking at getting that technology ready to deploy in the clusters in 2030, or at least by then anyway. But the programme funds up until 2025. So the focus of CCS Innovation 2, looking at mid-stage TNL levels between 3 and 5, so 1 tonne a day pilot research project as an example. Moving on through the TRL stages, we're then looking to get 100 tonne a day demonstration facility, and then we've had the study which we commissioned on next generation carbon capture. So that's really looking into developing capture technology as we've discussed today. And then just beyond 2025, this is our ambition to get a first of a kind facility up and running in the clusters in 2030, and then also develop other technology as well behind that. And to give you an indication of what we're looking at in CCS Innovation 2, we launched last May 2021. We started off with the next gen study, which I spoke about today. That lasted 9-10 months, and then we £30 million available in grant funding. We were selected in that, and they began funding in April. But now we're moving on to Co2, which is following on similar to Co1, but we've got the additional lot of funding for lot 3, and that's really focusing on the next generation carbon capture technology review, so that we can get site operators kind of having a think about how they can deploy some of this technology if they haven't thought about it before. We're looking at some of the dispersed locations and the challenges that they face there. So we're looking at funding feasibility studies. But in Co2, the biggest lot of funding for lot 1 and lot 2 is we've got £6.8 million available, and that should be for projects lasting as a maximum of 24 months. So for lot 1, it's for TRL 3 to 5, and you can apply for to 8. Now, applications do close on the and we held an engagement day on Tuesday earlier on this week, and the video of that will be uploaded to gov.uk shortly. And if you want to ask us any questions about the competition for lot 1 and 2, you've got until the 24th, which I think is tomorrow, to get questions in to us about a potential application or queries that you have. But really the focus, I guess, for this discussion is about the feasibility studies. So as I said, we want to try and use the outputs that we've got from this study, generate some discussion, some ideas with site owners and technology developers to see how we can start deploying some of the capture technology and develop it as well. I think it was Mark Summerfield that mentioned about energy from waste and applications to the biomass team about the for capture. The application deadline for that is the 2nd of December, and you can apply for up to £50,000 of grant funding. So we're looking to fund around about 10 feasibility studies that will last for about 12 months, and they will start from about, I'll just show you in the timeline schedule next. The feasibility studies will start around about June, July. So when the application closes in December, we'll go through assessment and moderation, and then we'll start the projects then. So just some information about the other lots, lot 1 and 2, deadline for questions tomorrow. We'll publish the Q&A on the 1st of July, which is anonymised, and the applications close on the 5th of August. For lot 3, that's extended because the applications don't close until December, so we've got until the 16th of September to submit any questions that you've got, and we'll publish that, closing on the 2nd of December. And just to give you an idea of some of the projects that we funded in Call 1, you notice some big names there, Baker Hughes, and if you're familiar with Sea Capture as well. Just looking at the capture projects, we've got Carbon Clean Solutions, they're looking at rotating packed beds. We've got Sea Capture, which are looking at deploying some of the technology at industrial sites. So they're kind of really looking at some of the kind of outcomes of what have been published in the study with their project. And then we've also got Keep Regeneration, which is SSC Thermal, which AECOM and UK CC SRC are involved in with that as well. And we get spread throughout the UK too. And it just gives you an idea of some of the projects that we fund, and there's more information about the specifics of it on gov.uk. Call 2, We've got £1.8 million available with ring fence for that. You can apply for up to £1 million, and if for lot 2, you can apply for up to £5 million. We've got £5 million for that. So the application deadline is the 5th of August, and then for lot 3, which is looking at the feasibility studies for next generation carbon capture to be deployed on industrial waste and power sectors. The deadline for that is the 2nd of December. And if you've got any questions for this, or if you want to have a chat with us or chat with anyone within UK government or within BEIS, please do get in touch with us at industry.innovation@beis.gov.uk. And that is it from me.
Great, thanks, John. Thanks for persevering through the slight issues with your internet connection. But yeah, thanks very much. So that concludes today's workshop. We might just about make it by 4 o'clock if I talk quickly through this last bit. So thanks very much to everybody for attending. Thanks to the speakers today. Thanks for engaging in the discussion and debate. The email address is on the screen there. John's just given you the BEIS contact details for industry innovation for any questions about the funding calls. If anybody has any other points or questions of interpretation or any other CCS related issues for AECOM, then the nextgen.ccus email address is the one to follow. As we've seen, and we're all aware, there's a number of current challenges around decarbonisation of energy intensive industries, and those are political, economic and regulatory as much as technical. But I don't think we can underestimate the value and importance of understanding and developing opportunities relating to decarbonisation and energy transition. So again, I'll go back to just thank everybody for your participation today and in the previous stakeholder engagement workshops. Your input, and particularly from the advisory board, has been invaluable in making sure the results of the study are relevant and appropriate to the industries that we've represented. Thanks also to the technology providers that have allowed us to use their products as exemplars in this study, and the advisory board for your input and guidance. And thanks to the BEIS team, Nick, John and Derek, for your active engagement all the way through the project. Again, we've making sure that we're delivering to meet BEIS's objectives in supporting the funding calls and demonstrating the technologies that are out there that might be applicable to decarbonising industries as we go into the next 10 or 15 years. I also wanted to thank John Gibbons of the University of Sheffield for your input and advice all the way through, and not least for chairing today. And I'd like to personally thank the AECOM team for their diligence and commitment in undertaking this work, in particular David and Stephen, Reese, Katie, Clem and Kevin, most of whom I think are on the call today. And also in the introduction I didn't manage to give, I was going to thank Caris and Mel at the UK CCSRC for managing and organising today's workshop and driving the Zoom call. So thanks very much, Joel. Thanks again to everyone for attending and participating today, and we'll close the call. Thanks all and good luck. Thanks very much. Cheers.